All right. Sorry, like my internet was cut off and I'm back now. Okay. Thank you for staying online. Okay, so let me start this again and share my PowerPoint slide here. All right. Can you guys see my screen here? All right, good. Thank you. So a couple of reminders here. So we're starting from this week. You guys will have labs. Okay. So lab 1 this week, it's basic measurement and then the uncertainty stuff. Okay, so you guys will be measuring a few different objects today, and then some of you guys on Thursday. Okay, and then also some volume and then mass measurement for water. A second reminder is homework 1 is due tonight. Most of you guys have done that. Okay, so if you haven't, make sure you do that by tonight. Okay, it's due by 11:59, just before midnight. Okay, so that's on those two. So last time we started chapter 1, chapter 2. Actually, we started introducing scalars and vectors. Okay, so basically the quantities that is can be expressed just by numbers with appropriate units, then they are scalars. And then for quantities that needs both magnitude or numbers with unit and direction, then they are called vectors. Okay. To express a vector graphically, you will draw a line, straight line with a starting point, which we call the origin or the tail of the vector, and then with the arrow on the other end, we call it the end or the head of the vector. Okay. And then in handwriting, you want to put an arrow on top of a letter if you use a letter for that. Okay. You can also use the subscripts. If you are going from one point to another point, then you can do point A to point B by using D, A sub A and B. So that means displacement vector from point A to B. Okay, basically displacement is a vector, and it's the change in the position of the objects. Okay, and then we talk about for the vectors, if you do numbers multiplied by the vector, then it changes the length. Okay, if the number is negative, then it also changes the direction of it by 180 degrees. Okay. If you move a vector parallelly to another location, then it's still the same vector. Okay, it doesn't change the vector itself. As long as you keep the magnitude and then the direction the same, then it doesn't change the vector. All right. So basically, you have to have, for two vectors to be identical, you have to have then have the same magnitude as well as pointing in the same direction. Okay, so this is some examples for two vectors, and then multiply a vector by a scalar. Okay, and if you have vector additions, you can use subscripts. As long as the second subscript is the same on the first one is the same as the first subscript of the second one, then you can cancel that subscript. So for example, d a sub b is equal to d a sub d plus d d sub b. Okay, we talk about this in class. And then this also apply to more than, if you have more than two vectors. The algebra of vectors in 2 dimensions, so it's called head-to-tail method or graphical method. So basically, you move the second vector parallelly to where when its tail is at the head of the first vector. Then the resultant vector will be pointing from the tail of the first vector to the head of the second vector. Okay, so that's how you do vector addition graphically. You can set up the coordinate system x and y, and then in that case, you can express your vector in components form. So then for a 2-dimensional vector, you will have an x component and y component. Okay, so basically you can this vector then is equal to its x component plus the y component. Okay, so ax is the x component, ay is the y component there. So you can express a vector in the form of a magnitude and a direction. Okay, so a, that's the magnitude of it, and then theta is the directional angle of it. You can also express a vector in its components form. Okay, so you can express a vector by saying its x component is what, say such as 3 meters or whatever, and then the y component is say 4 meters or whatever. Okay, but either way, if you are given information in either way, for example, you are given the information for a vector in its x, y component, you can figure out its magnitude and direction. And then vice versa, if you are given the magnitude and direction of the vector, you can figure out its x and y component. Okay, so by utilizing these two equations or those two equations, okay, depending on what's given or what are given. All right, the directional angle is defined as the angle between the vector and then the positive x-axis. Okay, it's called theta. So then in that case, you can see, I like to make one more comment about the theta. Okay, so theta goes from the positive axis and then counterclockwise to be positive. Okay, so if the angle is above it, then it's positive. Okay, so counterclockwise to be positive. If the angle is below the x-axis, then you can either do minus angle. For example, if this is 20 below, then you can say minus 20. Or you can do 340, right? Because if you go through 1 full revolution, then it's 340. Okay, so if it's below, then you do 360 minus 20. Okay, so either way, cosine and sine will take care of that. Okay, so because any angle plus 360 degree, if you do sine or cosine, it will be identical. Okay. All right. Now another sort of coordinate system is called polar coordinate system, where you are given in this case it would be identical to the magnitude, how you describe a vector. So it's given in magnitude and then direction angle. Okay, so r and phi here. If you are giving the polar coordinate system, that means you are given the magnitude of the vector and then its directional angle. Okay, although it's given in a slightly different notation, but r should be the magnitude and then phi should be the directional angle. So in that case, you are given the magnitude and the angle, you can figure out its x and y component. Okay, or the x-y coordinates. Okay. And last time we also talked about vectors in 3 dimensions. So in addition to the two-dimensional vector, you just add a third dimension. Okay, so that means add a third component there, the z component. Okay, a z component in the k direction, in the z direction. Okay, and then in that case, the magnitude of it will be square root of ax squared plus ay squared plus az squared. All right, and then the directional of it will be should be described by 2 angles, one in the xy plane with the x-axis, and then one in the z plane. In this directional here, so it should be the angle of this red here with this diagonal dashed line here. Okay, so but it's not mentioned in this textbook, so we will not go through the directional angle for 3 dimension here. Okay, but you can simply express a 3-dimensional vector by the components. Okay, so you can specify the 3 components, then that's sufficient enough. Okay, because then once the 3 components are determined, then the vector is determined. Okay. All right, so this is what we talked last time. Now today we are going to look more onto the algebras of vectors in this case. So last time we mentioned about graphical addition. Now this time we will talk about the analytical addition, okay, of 2 vectors or more, or maybe 3 vectors, etc. So for example, if you are doing vector A, okay, on the figure here on the left here, if you are doing vector A plus vector B, right? So basically, you move vector B parallelly over, so the tail of vector B will be at the head of vector A, then the resultant vector should be this C vector in dash, okay, in purple dash here. So this is your resultant vector. Now, doing vector addition analytically means we are looking at the XY component, right? So then you'll probably want to figure out what's the X component of this new resultant vector C, what's the X component and its Y component, okay? So if we are doing this analytically, so then we are using components, okay? So simply what you need to know is, the first thing you need to know is find the components of each vectors to be added. So A plus B, that means you want to find the X component of A, X component of B, and then Y component of A, Y component of B, okay? And then add the components separately, the X and Y components separately. So C new vector, C, its X component should be equal to the X component of A, AX, plus the X component of B, BX, all right? So in this case here on the figure right here, the equation show here. So X component of the new vector should be AX plus BX. And then its Y component should be AY plus BY, okay? So simply like that. So then you have new components for the new vectors, or the XY components for the new vectors, CX and CY. So once the XY components for the new or the resultant vector is determined, then you can figure its directional angle, okay, by taking the tangent inverse of the Y component of the C divided by X component of the C, okay? So then you will have both magnitude and then, okay, and then for magnitude, it should be the same like you are doing X component square plus Y component square and take square root, okay? So in that case, you will have your resultant vector determined, because then you will have the magnitude as well as the angle, directional angle, okay? And then if you are doing subtraction of vectors, okay, so say if you are doing A minus B, right? So then it's equivalent, you are doing A plus minus B, right? So minus B then will be the reverse, like the will be the vector B, you simply just reverse the direction, okay? So if you do that, so for B vector and then minus B vector, if you do minus B vector, that means for this minus B vector is simply you will have minus BX as its X component, okay, and then minus BY as its Y component, okay. So the sign will go to the components as well. So in that case, then the new the components for the resultant vector, the new vector will be for X component, it will be simply AX minus BX. Okay, and then for the Y component will be AY minus BY. Okay, simply like that. So again, if you are doing subtraction, then you want to figure out the X, Y, and components for the original vectors. Okay, and then you can use this to determine its new components, the components for the new vectors. Okay. So this is the analytical way how you want to do it. Now let's take a look at one example here, okay? So I will go through part A here on how to do the addition, okay? And then similarly, and later on when we look at that, after we look at that, I will have you guys work on B to do the vector subtraction, okay? So let's look on this part A first together. So I'm going to stop sharing the screen for right now, but you guys can pull the PowerPoint slide on your end, okay? So it's tiny URL at the bottom here, tinyurl.com/PHY2055-04, okay? So if you haven't pulled up the PowerPoint slide, you can do it now, because I'm going to stop sharing the screen. I'm going to use my camera and then piece of paper here to show the work to you guys, okay? I'm going to stop this now. And then I'm going to switch my camera. Okay. All right. Here we go. Okay. So So the problem stated that we have a vector A. So it's always good to sketch the problem, okay? So this is the XY coordinate system, X and Y, all right? Now it says there's a vector A has a magnitude of 40 meters and points in a direction 20 degree below the positive axis, okay? So that means somehow here, so you want to do the sketch as best as you can. So let me just try to do that. So this is a vector A, okay? This is 20 degree below my x-axis, all right? Now it says there's a second vector B has a magnitude of 75 meters and points in a direction 50 degrees above the positive axis, okay? So this is x, and then 50 is a little bit over half of 90, okay? So then somewhere here, so let me do just like that, okay? So this is B vector, all right? This is my B vector. So this is 50 degrees, okay? And then it's 75 meters long. So roughly about twice of A, okay? So you can indicate this is 40 meters on A and then 75 meters on B, okay? So, so what we know here is, so for the magnitude of A, this is 40 meters, okay? So when you are writing the magnitude, it's just the letter without an arrow, okay? So A, that's the magnitude of A is 40 meters. Now the directional angle of A vector, so let me use theta sub A, okay? So theta sub A is the directional angle. It says it's 20 degrees below, so that means it's minus 20 degrees, okay? You can do that. So if it's below, you can do minus 20 degrees. And then for vector B, it has a magnitude, so you can use letter B for the magnitude without arrow. It's 75 meters, okay? Its directional angle, it's 50 degrees above the x-axis. So that means 50 degrees, okay? Positive 50 degrees, all right? So we are given the magnitudes of the two vectors and their directional angles. So to do the vector addition analytically, you want to figure out their x and y components first, right? The two vectors, if you want to add them up, you want to figure out the x and y components first. So you need to figure out ax first, ay first, and then bx, and also by, okay? So according to the components of the vector, it should be equal to its magnitude times cosine of theta a, okay? So this is 40 meters times cosine of negative 20 degrees, all right? So this will give you 37.59 meters, okay, on the x component. Now, if you notice that all the quantities are given in three sig figs originally, so that means I should put three figs here: 40.0, 20.0, 50.0, 75.0, okay? So then we should keep at least 4 digits during our calculation here, okay? So let's keep 4 digits here for right now. The same for its y component, it should be magnitude times sine of the directional angle. So 40.0 meters sine of minus 20.0 degrees. Okay, so that gives you minus 13.68 meters. Okay, you can do the same for vector B. So its magnitude, it should be B times cosine theta B. Okay, but I'm going to just put the magnitude here. So this is B, and then cosine of 50 degrees. This is theta B, okay? So then this one would be 48.21 meters, okay? I think I have the correct numbers here, okay? But in case if you have a different number from your calculators, first thing to make sure you have your calculators set in degrees, okay? Because we are using degrees here. And then if you still have a different number, then let me know. I might have it wrong because sometimes I also make mistakes. Okay, so on this one it's B again, 75.0 sine of 50 degrees. Okay, so that would be 57.45 meters. Okay, now we have xy component of A and then xy component of B. Okay, so then for the new resultant vector C, so I put the arrow on top. Okay, let's see. So Cx will be equal to A plus B. With arrows, that means vector addition. But I will be looking at the components. X components should be just Ax plus Bx, right? So in this case, you'll be doing 37.59 plus 48.21 meters, which gives me 85.80 meters. Okay, its y component then will be Ay plus By. Okay, equals to minus 13.68 meters plus 57.45 meters, which will give me will give me 43.77 meters. Okay, all right. Now I have the two components. I can determine its magnitude, x square, y component square, 85.0 meters square plus 43.77 meters square, and then take square root of it. Okay, so less than will be 96.32 meters. To keep appropriate sig fix, so it's 96.3 meters. Okay, for the magnitude, its directional angle should be tangent inverse of cy over cx. Okay, so tangent inverse of 43.77 meters over 85.80 meters. Okay, that will give me 27.03 degrees, roughly 27.0 degrees. Okay, all right. So on here, on the graph here, you can kind of do this way. So if you are doing A plus B, you can put B, move B parallel over here. Okay, so it will be something like this. Okay, this would be B vector, then your resultant vector will be in kind of in that way. Okay, so C vector in that sense. Okay, yeah, kind of like that way. So yeah, 27 degrees. So from your figure here, you can see it kind of makes sense. Okay, this is a very rough sketch, but it kind of represent the your answers here. So about half of the angle, 27 degrees, and then a little bit longer than the B, the 75. Okay, so that sounds like we have the correct numbers for its magnitude and the directional angle. Okay. Questions for you guys? Just unmute yourself and you can speak up.
Excuse me, I have a question.
Sure.
It could just be misinterpreting the sketch, but wouldn't the B vector start at the origin? Or okay, so it would start at the tail or head of A, correct?
Right. So originally it starts from the origin, right? But when we are doing the two vector addition, we move it parallelly over intentionally, so its tail is at the head of the first vector.
Okay,
Yeah.
thank you.
Okay, and then my sketch is rough, so it doesn't probably doesn't have the right scale, but somehow it looks all right there. Okay. Other questions anyone else might have? If not, then I'll have you guys do part B here. So whatever I have on over here, it should be, you can still use the components, okay? For part B, you don't have to recalculate the components for A vector and B vector. And then for part B, you are looking for D vector equal to A vector minus B vectors, okay? So you'll be doing pretty much the same thing, change the positive sign to negative sign, okay? And doing the calculation here. And again, once you have your answers, click on the PowerPoint slide, you can submit your answers, so I will be able to see it, okay? All right, so many of you guys have some your responses. I'll wait another 30 seconds or so before we look at the solutions together, okay? All right, so if you haven't submitted your response, you can continue to do that, but we will look at what we have for right now. So it looks like you all agree with the magnitude, okay, 71.9, okay? That's also what I get, so 71.9 degrees, okay? So that's the magnitude. And then on the directional angles, many of you guys says 81.5 degrees, and then a couple different responses, okay? So let's look at the directional angle, okay? Or let's start with the components, okay? I'm going to stop sharing my screen here so you guys can see my work on the paper. All right. So I think probably you guys all get the components right. So dx will be ax minus bx, okay? And then you plug in the numbers, you will get, let me see, I will just skip plugging the numbers, minus 10.62 meters on that one, okay? dy is equal to ay minus by. Okay, plug in the numbers, we will get minus 71.13 meters on that one. Okay, so then for the magnitude, you do square root of x component square plus y component square. Okay, so minus 10.62 meters plus minus 71.13 meters square, and then take square root of the sum of the two. We will give you 71.92 meters, which is roughly 71.9 meters. Okay, so we all agree with that one. All right, now let's look at the directional angle. So it should be tangent inverse of the y components over the x component, right? So then tangent inverse of, you are doing minus 71.13 meters over minus 10.62 meters, okay? So if you plug in all this into your calculator, it's going to tell you 81.5 degrees, okay? But let's take a look, okay? Let's take a look, if we draw a sketch here on somewhere here, let me put here. So I'm going to again do my A vector here, about 20 degrees below, and then my B vector somewhere here. Yeah, 75 and then 50 degrees, okay? So if I do A minus B, that means I'll be doing A plus negative B. So negative B, that means you'll reverse the direction of B, okay? So it becomes this one. This is negative B. This is B. All right, in that case, now if you are doing A plus minus B, so then you move this guy parallelly over, okay? So I probably just something like this, probably. Okay, so you'll see then, yeah, I think this is a bit longer. Okay, I know what it should be, so I'm going to just cheat on this here. So then this is my minus b, so the resultant will be this guy. This will be my resultant, the d vector. Okay, so from the sketch here, if so that's why I think you have to do the best you can do according to scale. Okay, make the angle. So the best way to do this is use a ruler and protractor, so you can get the scales right and then also the angles right. Okay, but this is what you should have. So you can see your vector is over here. If you are getting 81.5, that means the angle is somewhere here. So this is your resultant vector, okay? So apparently that's not the case. So 80.5 doesn't seem to be right over here, right? Now, if you remember last time when we say after you plug in your numbers in your calculator for the angles, you want to double check your x component, right? If your x component is less than 0 or negative, then what do? You add 180 to your final answer, okay? So because of that, you add 180. So then it's 261.5 degrees, or roughly 262 degrees, okay? So 262 then will be corresponding to this directional angle, right? Less than 270, okay, but 262, all right? So that's the key. I'm glad that you guys get the 81.5 degree right, okay? And I'm also glad that you forgot that, because now you know if your dx is less than 0, you want to add 180, okay? So it's better you make mistake right now than making mistakes during the test, okay? So pay attention to the x component. If it's less than 0, you add 180 to it, okay? I did see there's one correct response, okay, among your submissions. As the first one here. So this says 98.5 degrees below x-axis. Okay, so this one is valid too. Okay, this one is fine too, because that means you are indicating this angle below. So you're mentioning it's below, so it's this angle. Okay, so that's fine. You can express in that way. Okay, so the first one actually is correct. Okay, so whoever submit the first one, you are right. Okay, as well. So it's either 262 or you can say 98 degrees below x-axis. Okay. All right. Now questions you guys might have. Okay. So if not, then let's move on here. So that's the analytical way how to add the two vectors. This also applies if you have more than two vectors. Okay, if you have three vectors, then you add the x component of the three vectors up, and also for the x component of the resultant, and then the y components of the three up for the resultant. Okay. Similarly for 4 and 5, etc. vectors. All right. If you have combination of plus and minus, you do the same. Okay, so whatever you encounter plus, you do plus, add the component, and then minus, you subtract the component. Okay. Another way how to do vector addition analytically, this is not in the textbook. Okay, but we'll talk about this here as well. So this is utilizing the laws of sines and laws of cosines. Okay, so let's have a review on law of sines and law of cosines. Okay, so law of sines, this is referring to if you have triangle, so ABC here, triangle ABC. All right, so the angle that is attached to point A is called angle A, and then angle B here, and then angle C here. All right, and then lower letter ABC, that means the length of the sides. Okay, so this one is opposite to angle A for A, length of A, and then B, length of B is opposite to angle B. Okay, and then C is opposite to angle C. So law of sine says if you do sine of the angle A over the side of the opposite, okay, to the angle, so sine A over A should be equal to sine B over B, should be equal to sine C over C. All right, that's law of sines. And most of the time, you just need two sides of the equation. Okay, you can set sine of A over A equal to sine B over B, or you can do sine A over A equal to sine C over C. Okay, or sine B over B equal to sine C over C. Law of cosine says C squares, okay, the opposite end squares, opposite side squares, the length of it equal to a squares plus b squares minus 2 times a times b times cosine c. Okay, that's law of cosine. Okay, now it also applies to if you are putting a, if you are looking at this side, so a square should be equal to b square plus c square minus 2bc cosine a. Okay, in that sense. All right. And then also for this side as well, if you do b square, that should be equal to a square plus c square minus 2ac cosine b. Okay, so that's law of cosines. All right, now let's see how we can utilize these two laws for vector additions. Okay, so for example, let's say you have vector 1 in this figure here, the blue vector, which is the first vector, and then you have the second vector, vector 2. So if you add vector 1 plus vector 2, then you get the resultant vector r. Okay, resultant vector. So then if you are given the magnitudes of v1 and v2, all right, and then its directional angles. So v1 has a directional angle of 60 with respect to horizontal to the right. Vector 2 has a directional angle of 140 degrees with respect to positive x horizontal to the right. Okay, so then what would be the magnitude of r and then its directional angle? Okay, so we can use law of cosines to figure out this magnitude, right? The length of r, because this is a triangle here. If you do v1 plus v2, now you place the tail of the second vector on the head of the first one, then the resultant points from the tail of the first vector to the head of the second vector. Okay, and this is, in this case, it's given, it's not listed here, but it's given that v1 is equal to 100, the length, v2 is equal to 130. Okay, so then you can apply, so instead of doing the x and y components of v1 and v2 and then add them up to get the resultant vector, you can apply law of cosines directly to get the magnitude of r, right? So you can say r squared is equal to v1 squared plus v2 squared minus 2v1 times v2 cosine of this angle. You have to figure out what the angle is this, okay? Because this is 60 degree, that means bottom half of this angle is 60. This is 140, that means this is 40. This is 40 is 180 minus this guy, right? Because straight line is 180 minus 140 gives you 40, okay? And then this is a horizontal line, this is horizontal line. So if this is 60, then this is also 60, okay? So then you figure out that V1 and V2 has an angle of 100 degrees, which is 40 plus 60, okay? So between V1 and V2, the angle theta is 100 degrees. So you plug in the numbers, you can figure out the magnitude directly, okay? For R vector, the resultant vector, all right? Now, once you have that length, you should be able to figure out this angle, alpha here, right? By looking, because now you know the length of 3 sides of the triangle, and then you know this angle. So you can utilize the law of sines now to figure out this alpha angle, all right? So sine of alpha should be, you do sine of alpha over the opposite end, opposite side, V2, it should be equal to sine of this 100 degree over r, right? So sine alpha over v2 is equal to sine 100 over r. Then you can solve for your r, because you know v2 is 130, okay? R is 177.24. You just plug in the number, solve for r, okay? So first, a couple of steps of algebra here, but it's doable, okay? So you can solve for your r alpha, which gives you 46.25 degrees there. This alpha is 45.6.25 degrees, All right, then the directional angle for the resultant vector with respect to the horizontal, it should be this alpha plus the 60. Okay, so 46.25 plus 60 will be the directional angle for the R. Okay, so 106.25 degrees. Okay, so so either way, you can do the components method or you can use law of sines and cosines. Okay, whichever you feel like most comfortable doing, it should get you the correct answers for the magnitude and directional angle of the resultant. Okay. All right. You guys will get some more practice in lab as well. I think it's the fourth lab. Okay, it's still a couple weeks from now, but there's that one in the lab as well. Any questions you guys have? Okay. So if not, we'll take a look on an example on how you can use law of sines or cosines to solve for a problem associated with vector additions. Okay. So this one says if you have two vectors A and B, they are having identical magnitudes of 5 units. Okay. And then A plus B is equal to A vector plus B vector is having 5 times square root 2 units in j direction. What will be the angle between vectors A and B? Okay, I'll give you guys a few minutes to try to see if you can solve this one. Okay, it's okay that if you couldn't, but then we can look at the solution in a few minutes together. Okay. So I will list the knowns for this one. This one we know that A and B have the same magnitude. Okay, so A and B without arrow, that means the magnitude is 5 units. It tells you C vector is equal to A vector plus B vector equals to 5 times square root 2 of J in J direction. Okay, so that means this is C vector. It's in the Y direction. C vector, which is equal to A plus B. Okay. It's asking you what would be the angle between vectors A and B. Yeah, if you have an answer, you can submit your answers by clicking on the problem. Okay. All right. So we only have about 5 minutes remaining. Let me go through how you want to solve for this one. Okay. So let me stop sharing my screen. You can see my work over here. Okay. So C that is there. So you want to do A plus B. You can say, okay, if A, now I'm going to just again cheat on this. I'm going to say this is my A vector. Okay. And then if I do A plus B, so that means B is this here. I place the tail of B at the head of A, so then it's pointing in that direction. This is B, okay? So A plus B will give me my C, okay? And then because I know, I apologize for my internet, but I'm back here. So A plus B, okay, will give me my C, all right? So in this case, it tells me my A and B is having length of 5 and 5, right? And then my C is 5 times square root 2. So C is 5 square times 5 square root 2. 5 times square root 2, okay? So then I can utilize law of cosines here by setting up that C square equals to A square plus B square minus 2A times B cosine of the angle that I'm looking for. I'm going to just call it theta, okay? You can call whatever you want, but then I can plug in the numbers because I know A, B, and then C. C is 5 times square root 2. So 5 times square root 2 square equals to 5 square plus 5 square minus 2 times 5 times cosine theta, right? So I'm going to apply my law of cosines here. This one will give me on the left here 5 square will be 25. Square root 2 square will be 2. So 25 times 2 will be 50. Okay. And then this is 25 plus 25 minus. So 2 times 5 gives me 50 cosine theta. All right. You'll see that 25 plus 25 will be 50. So then 50 and 50 will cancel out. So it will tell me that 0 equals to minus 50 cosine theta, okay? Which means cosine theta will be equal to 0, right? Then I can solve for my theta. So then theta should be equal to cosine inverse of 0. You take cosine inverse of both sides, okay? Cosine inverse of both sides, okay? So cosine inverse of 0 will tell you it's going to be 90 degrees, okay? So the two vectors then makes an angle of 90 degrees here, okay? So if we use law of cosines here, this one, it's going to be easily determined here, all right? Now the key here is you can see is you want to put a sketch, okay, of the problem like that. So you'll see what to use, okay? So once you have everything known factors indicated on your sketch, you probably can should be drawing a larger figure than I do here to see it clearly, okay? All right. I'll stop here for today. Any questions you guys might have? All right, if you guys have no questions, then I will see you guys tomorrow in the lecture, okay? Remember, most of you guys have lab this afternoon, okay? Enjoy the lab. See you tomorrow.
Thank you.
You're welcome. See you.